All right, let's talk about enzyme kinetics, specifically Vmax and Km. Now, if you've ever studied biochemistry, you know these terms can feel, well, a little abstract, right? Just numbers on a graph. But what if they're actually as simple and intuitive as running a factory? Today, that's exactly what we're going to do. We're ditching the textbook to see what these things really mean.
No, seriously. For the next few minutes, just push those graphs and equations out of your mind. We're going to build a really simple mental model that makes this all crystal clear. No heavy memorization required, I promise.
So let's take a little field trip. We're going to a tiny, incredibly efficient factory that's running inside every single one of your cells right now. This little analogy, it's the key. It's going to unlock everything about Vmax and Km.
So, here we are. Welcome to the Enzyme Factory. This place has one simple job. Take in some raw materials and turn them into something the body desperately needs. It's a dedicated, single-purpose production line. And if we can understand how this factory works, we'll have enzyme kinetics totally nailed.
Okay, first, let's meet the key players. The factory itself, that's our enzyme. The raw materials it needs to do its job, that's the substrate. And those finished goods it ships out the door, that's the product. Factory, materials, goods. Enzyme, substrate, product. Simple, right? Keep that in your head as we move on.
Now for our first big concept. You know, every factory has a top speed, right? There's a physical limit to how much it can possibly produce in a day. Well, in the world of enzymes, we call that limit Vmax.
The production line itself is pretty straightforward. First, the raw materials, our substrate, they show up at the loading dock. Then, the workers inside, and you can think of them as the enzyme's active sites, they get to work processing everything. And finally, the finished product gets shipped out. Easy.
So at first, obviously, the more raw materials you deliver, the faster the factory works. But let me ask you this. What happens if you just keep dumping more and more truckloads of materials at the front door? Does the factory's output just go up and up forever?
No way, right? Of course not. Eventually, you hit a bottleneck. Every single worker is busy. Every station on the assembly line is already cranking away. The factory is running at full tilt, 100% capacity. It is completely saturated. You can pile up a mountain of raw materials outside, but it won't make the production line go any faster.
And that right there, that moment, that is our first big term. That peak production rate, the factory's absolute unchangeable speed limit, that is Vmax. It's the maximum velocity an enzyme can hit when it's totally swamped with substrate.
Now, if we just peek back at that classic graph for a second, it suddenly makes perfect sense. The y-axis going up, that's our factory output. The x-axis going across, that's how much raw material we're adding. See how the line goes up and then flattens out? That plateau, that ceiling it hits, that's Vmax.
All right, so we've got the factory's top speed figured out. But what about its efficiency? You know, how motivated is it to even get started? This brings us to our second concept, Km, which I kind of like to think of as the factory's appetite. So the textbook definition of Km is actually pretty simple. It's just the exact amount of substrate you need for the enzyme to work at half of its maximum speed. So get this, Km isn't a measure of speed, it's a measure of how much raw material you need to get the factory humming along nicely. To make this super clear, imagine two different factories. The first one has a low Km. This factory is eager, it's efficient, it only needs a small pile of raw materials to get going at half speed. Then you have the second factory, with a high Km. This one's, well, it's kind of picky, a bit reluctant. It needs a massive mountain of materials just to get to that same half speed point.
And that is the absolute key to understanding Km. It's not about speed, it's about attraction. Or, in scientific terms, we call this affinity. A low Km means the enzyme has a really high affinity for its substrate. It's like a magnet. It just wants to grab it and get to work.
This gives us a super simple rule, and it's an important one to remember because it's an inverse relationship. A low Km means a high affinity. The enzyme is very attracted to its substrate and binds it really tightly. A high Km means a low affinity. It's less attracted and doesn't grab on quite so well. So, okay, we've got the factory's top speed, Vmax, and its appetite, Km, but why does any of this actually matter outside of an exam? Well, because understanding these little enzyme factories is absolutely fundamental to both biology and modern medicine.
Knowing an enzyme's Vmax and Km is huge. It lets scientists figure out how our metabolism is controlled, predict how our cells will react to different conditions, and, maybe most importantly, design incredibly effective drugs. These aren't just abstract numbers. They are the control knobs for the machinery of life.
And here's the perfect real-world example: drugs. So many of the medicines we rely on are actually enzyme inhibitors. They're designed to get into these tiny factories and just gum up the works, either by messing with the top speed, the Vmax, or by killing the factory's appetite for raw materials, changing its Km.
So, the next time you see one of those Michelin-Menten curves, I want you to do me a favor. Don't just see a graph. See this factory. This mental model is your key to just getting enzyme kinetics without ever getting bogged down in the math.
Let's lock it in with one final blueprint. Vmax is the factory's top speed. It's a measure of speed. Km is the factory's hunger, its appetite. It's a measure of affinity. That's it. That's the whole shebang. You got it.
And that's really all there is to it. Thinking with analogies like this can just unlock so many complicated topics. So, I'll leave you with a question to chew on. What's another really complex system, could be in science or anywhere else, that could be made totally simple if you just found the right analogy? Think about it.